So guys, before we go into the presentation, I need to take a few moments to introduce GMI, why we're here, what we do. Let me see if I can do that, because normally Bob runs the presentation. So here we go. Here we go. So here you can see about us, as you know about Bob, I just told you, and I'm Paolo, I'm the VP of Sales of GM International, or GMI. And as I said, our company, so we are a safety company. We design, engineer, and manufacture a complete range of IS, intrinsically safe and seal certified devices, which are used in automation packages such as DCS, ESD, SCADA, marine, all kinds of package, HIPS, PLC, in several industrial sectors, from oil and gas to food and bev. We have over 40 years of experience, and we're very proud to manufacture all our product in our facility near Milan, Italy. In Italy, we don't only make gelato or Ferraris, we also make IS barriers. On the other hand, we are global players with presence in all the continent. We have about 10 offices and over 75, actually now is over 95 distributors, about 200 people. We run many courses along with the webinars. Also, we do functional safety product. We take special care in manufacturing them, using state-of-the-art technology. We have 100% traceability, 100% testing. We offer 5 years warranty. We are certified globally, because at the end we care, because our product protect the plants they are installing and the life of the people that, in the plants and nearby the plants. Here is our certification. 100% committed to global standard regulations. They change every day. Bob, nowadays I spend all day looking at the sanction in Russia, which basically say we cannot sell in Russia any longer. And I have just, unfortunately, to send a mail to our Russian team, say, hey, we have to stop selling. So there's a lot of rules and regulation we have to follow, but typically we are certified, for EX certification by over 15 agencies. We have TUV functional safety management, ISO 9000, ISO 45000, ROS, REACH compliance with code of ethics, and so on. These are the products we manufacture: IS barriers, safety relays with and without line monitoring, isolators, also seal certified, some power supply, EX and seal certified, multiplexers, harsh multiplexer, termination panels, SPD or surge protection, loop indicators, and as I mentioned earlier, a division that runs training, for and education. Some of our customers, lots of customers all around the globe. We have a lot of OEMs which we are proud to supply to, because they install our product in their machines, rigs, which are typically placed in very rigorous environment. And our products are very, very reliable. So that's it. That's about it. So Bob, since I'm running the presentation, you just give me a nod or something, and I will move on to the next slide. Okay.
Sounds good.
Great. And just one last question, guys. At the end, there's a question and answer box there. You can, anytime type in your questions, and we will try to answer either at the end or as we move along. Okay, Bob, it's all yours. Let's go to the first slide.
Okay.
Which is this one.
Thank you, Paolo, and thank you very much for everybody putting up with me being a little bit late here. We're having some internet issues, and so I'm actually currently at a client's location. We're doing an IEC EX COPC course for these guys up in Tyler, Texas. So we're taking a break. It's good time. It's lunchtime actually here in Houston, or actually in Tyler. So get this opportunity to do this. So to cover everything in 40 minutes is a lot of material, so we'll just dive into it. I realize some of this is probably basic, but some of you may not have much exposure to EX. So we just want to kind of go through some of the fundamentals, and then we'll get into some questions and answers that some of you guys have asked that are a little more detailed. And certainly as we go along, please feel free to ask any questions. So explosive atmosphere types, basically, no matter where you are in the world, we treat explosions or explosive atmospheres in a similar fashion, no matter what the regulations are. We have gases, vapors, mist, we have combustible dust, and then we have ignitable solid particles. And all three of those in proper mixtures and proper ratios, when we combine that, we can have an explosive atmosphere. And so anytime that we're taking electrical equipment and we're starting to put that in there, as well as mechanical equipment, we need to address that in providing certified products or solutions. Next slide. So flammable and combustible liquids can produce gases and vapors, which are also combustible. They're easily ignitable and very dangerous, given that they can spread quickly and widely. So all flammable liquids which are at or above their flash point will give off combustible vapors. So the important point to remember here is the term flash point. Flash point is that point in which a liquid, so if we have say, for example, liquefied natural gas, at the point in which it starts to emit vapors, that is considered to be the flash point. Sometimes people get confused with flash point versus ignition temperature. The ignition temperature is the temperature in which it will spontaneously ignite. So flash points are always lower than the ignition temperature. Next slide.
Yep. Oops. What happening here? Okay, here we go.
There we go. And there we go. Flash point is that temperature which an ignitable amount of gas is emitted from a liquid. So combustible dust can be any part of the following types of material: metal dust, carbonation dust, flour, grain, wood, plastics, and chemicals. Some of you may have seen a video that's kind of gone viral here and actually looked very much like, what's going on in Ukraine right now. But it was a coal dust explosion that took place in Pakistan. It was an entire facility that was leveled based upon coal dust. And I can pretty much assure you they haven't figured out exactly what transpired, but it looked as if it started in an area that was a transportation conveyor belts. And most likely it was probably some overheating of some bearing. And when we have dust explosions, they can be just as volatile, just as dangerous, just as deadly as gas explosions. So we always think of the oil and gas industry or the petrochem industry as being certainly flammable atmospheres, but we cannot forget that there's other potential dangerous atmospheres out there that we have to address in some way, shape, or form. Next slide. So in order to have an explosion, right, we have to have obviously a source of ignition. We have to have the explosive material, the fuel, and then we have to have air or oxygen. And so every explosion that we have, for the most part, there are some exceptions to this, but for the most part, we're going to have we're going to have all three legs of the triangle. Now, the sources of ignition can be many different potential sources, which we'll talk about here in a bit. Next slide. So what are the common ignition sources that we need to be concerned with? Some of these, again, are applying to electrical equipment, but some of this applies to mechanical equipment as well. So things like hot surfaces, again, bearings, engine exhaust. We had a big explosion here in South Texas about 16 years ago with the BP Texas City, and actually the source of ignition there was actually the diesel exhaust from a truck. That was actually the source of ignition. Broken, damaged parts, obviously lightning. And then, of course, things like open flames, fires, cutting torches, cigarette lighters, pilot lights. One thing that people don't think about is actually mechanical sparks. Obviously, grinding and cutting, we create sparks, but even drop tools or equipment, that can create a thermite action. So depending on the type of material, the tool that you're using in a flammable atmosphere, that actually can create enough energy to ignite that flammable gas. Next slide.
Yeah, here we are. You see it, right?
Not yet. I may be.
Sorry.
Here we go. No, I see it. I see it. Stray electrical currents are certainly a big one. Welding electrical faults could be grounding issues. It could be besides just the normal arcing and sparking that we would normally find with contactors making or breaking or all that. Static electricity is another big one that people overlook. Anytime when we're moving materials, dust, liquids, anything like that, and we're putting it into containers or taking it out of containers, we can actually create static electricity. So we have to be concerned with that. And certainly radio frequency, lasers, radio transmitters, telephones, all of those can potentially create enough energy in which we can ignite a flammable atmosphere. Next slide.
Batteries.
There we go. I see it. I'm a little delayed here.
I have to anticipate you.
There we go. So batteries certainly, if you take steel wool and put it against the two posts of batteries, or if you just touch them yourself, you can actually get enough little shock there. Not something that I would recommend doing, but certainly that's an issue. Ionizing radiation, that actually is a potential source of ignition, ultrasonics, and then certainly exothermic reactions. So again, when we think about hazardous areas, we think of the obvious sources of ignition, right? We think about electrical arcing and sparking, but in reality, we really do need to consider all of these other potential sources of ignition when we're doing our HAZOPs, or we're doing our analysis of our facilities, to make sure that we're making sure that we're not taking in equipment into those areas that potentially could create an explosion. Or certainly, how is the design of our process? What are we doing to minimize the effect of all of these? So ignition temperatures is one of the first things. We talked about flashpoint, but every gas, every flammable gas, we will assign them an ignition temperature. And for example, hydrogen is a very commonly used fuel, and it's becoming much more popular. People are talking about using hydrogen as a fuel, and it is a very efficient means of fuel. One of the benefits of hydrogen is actually it has a very, very high ignition temperature, means that it takes a fairly high temperature. One of the downsides of hydrogen, however, it doesn't take an awful lot of energy to ignite hydrogen. And hydrogen also has a very, very broad range of lower flammable limit to an upper flammable limit. So hydrogen is one of those gases that is very dangerous. However, from a temperature standpoint, it's actually one of the easiest gases to deal with. All these other gases you will see that we've categorized, and we put in behind them either Roman numeral 2C, 2A, or 2B. This is categorizing these gases based upon IEC standards, the 60079-10-1, which categorizes gases that have similar characteristics, and we kind of group these gases as opposed, so it makes it easier for selection of electrical equipment or mechanical equipment in hazardous locations to make that determination. Next slide.
It's coming.
Yeah, it's coming. There we go.
It's gas crew.
So we talked about this just on the last slide where I talked about it. Gas groups, ignition energy. Notice that hydrogen in microjoules, it only takes about 19 microjoules to actually ignite gases or hydrogen gas. So hydrogen, even though it is a very efficient gas, it's a clean gas, right? It is also a gas that is very, very, very easily ignitable. It doesn't take an awful lot of energy to ignite hydrogen. So literally 19 microjoules, if I was sitting in an environment that was hydrogen rich, and I was standing on a floor that had carpet and all this good stuff, and I started rubbing my feet together and lifted my feet, if there was enough hydrogen in that environment, I could actually ignite it by just the static electricity caused by my feet rubbing against carpet. So hydrogen is very, very dangerous, but it is something that certainly the world is looking at as an alternative fuel source. This is also another chart that gives you an indication about hydrogen in particular. And I don't want to discount the use of hydrogen, because hydrogen, when properly used, is an extremely efficient fuel source. However, I think a lot of people are thinking, wait a minute, what are some of the dangers with hydrogen? This chart is actually showing us the range of where hydrogen fuel air mixture, that if we have hydrogen in those quantities, we're going to have a potential ignition source. And every gas has what is called a minimum ignition energy curve. And what this chart is basically telling you is that if we have in an environment approximately 29% of hydrogen to 71% of air or oxygen, it's going to take about 19 microjoules to set it off. So it's a fairly high amount of hydrogen. You'll notice on the left-hand side, there's propane. Propane has a very narrow band of a lower to upper flammable limit, and it takes a little bit more energy to ignite propane. So propane is a little bit easier to deal with. Hydrogen is a little more difficult to deal with.
Okay, I guess we have a poll question here, Bob. Let me see if you can launch this. So for you guys, Bob talked about flashpoint, and we're going to ask you, make sure you're not asleep. What is the definition of a flashpoint? Can you see the poll, Bob? Yeah,
I can see
people
it.
start to answer.
I can see it.
Temperature in which a gas or vapor will spawn off the chart. But,
I'm sorry, Pablo, my thing got held up. You may have asked me a question. I didn't hear.
No, I was just saying that the last answer sounds a little bit, not off the chart. I said, the point is solid. We're talking solid and liquid. We're talking about gases. So I guess this could be the wrong answer. But I think I have a good idea because I have listened to Bob. All right. So a few more answers are coming in. Let's give it one more moment and then we cut it off because we, as you said, we are in time is of essence today. Okay, we have about 75% of you answered. So let me end the poll and show you share the result. So the majority answer B, or the second answer, right?
Right.
So,
right.
Which is the correct answer, correct, Bob?
That is correct. Yeah, that's where the flammable liquids will actually start turning into a vapor, if you will. So the A would be the ignition temperature, B would be certainly the flash point.
Okay, great. So you are listening, not all of you, but some of you are. Okay, let's move forward. This is T classes. You can see that?
Yep, I can see it. Thank you very much for forwarding that to it. So,
well, I'll tell you guys, you gotta pay attention because there'll be some question on this one.
There you go. Yeah, that's true. And so T classes, we hear this term used quite a bit. And what this is basically telling us is that every gas or vapor will have assigned a temperature class, and it'll be something from T1 through T6. And T1 is exactly 450 degrees C, T2 is 300 degrees C, and so forth and so on. So electrical equipment will actually also be assigned a Tcode. So part of the reason why we need to know ignition temperatures of gases and vapors is to make sure that whatever electrical or mechanical equipment that we're going to put in that environment will not exceed the ignition temperature of the gas or vapor present. So I think the next slide actually may give a little bit easier understanding of this one. So if you can forward that, actually, I think maybe the further on. So if you see there, right, hydrogen actually, as we focused before, hydrogen is a 2C gas, but it's a T1 gas. And remember, if you think back on that slide, what I said, hydrogen's ignition temperature was somewhere, I think it was 560 degrees C. T1 reflects 450 degrees C. So any gases or vapors that have an ignition temperature above T1 will fall as a T1 gas, so to speak. Most of the gases and vapors that you will find, about 99% of the gases and vapors used in industry will be somewhere between a T1, T2, or T3. There's a handful of gases and vapors that have very low ignition temperatures. Carbon disulfide is one of those gases that is the lowest, and it has an auto ignition temperature or ignition temperature of actually 90 degrees C. So it is very, very difficult to deal with. Next slide.
Okay.
I'm back. Okay, so temperature codes. This chart over here on the right-hand side is, I realize it's a little bit difficult to see, so I'll try to explain it. And matter of fact, if you go down to the third paragraph, so as an example, a product that carries a T4 rating, and if we look in the chart, T4 reflects 135 degrees C. So that means that any gas that's a T4 gas will have an ignition temperature of above 135 degrees C. However, it'll be below 200 degrees C, which is a T3. So it's somewhere in between. A T4 product will mean that that product on its relevant surface will never exceed 135 degrees C under its maximum ambient in which it's rated. So if I have a flame-proof motor and it's rated T4 and its maximum ambient is, say, 50 degrees C, the relevant surface on that motor is exterior to the motor. It will never exceed 135 degrees C. Therefore, I can use that motor in any environment in which the gases are T4, T3, T2, or T1. I could not use that motor in an environment where the gases are T5 or T6. Hopefully that makes sense.
Yep.
Next slide.
The next slide on density.
Yep. Another factor in which we get into area classification is the density of the gases and vapors. So when we get into area classification requirements and we start looking at what is a zone 0, zone 1, zone 2, which I know I haven't talked about, but I assume most of you are familiar with, we also have to take into consideration the density of the gases and vapors in the environment. So hydrogen being lighter than air, it has a density less than 1, will obviously go up near the roof, or if it's in an outdoor environment, will be dispersed into the atmosphere. Other gases, things like propane or gasoline vapors, are heavier than air. They will collect near the floor. So our area classifications will change based upon the potential flammable gases that we could see in our process facility. Because area classification is determining the likelihood and the potential amount and likelihood of gases and vapors or dust that could be present in a particular environment for a prescribed period of time. So we want to make sure we understand that going forward. So in this chart here, you can see that we've got a pipe. We have a potential source of release with those flanges, and we want to place some gas detectors. Well, it depends on where we would place those gas detectors is based upon the density of the gas in which it is in that process pipe. So if it's heavier than air, we put our gas detectors down in lower areas. If it was lighter than air, then we would put them up near the roof. If obviously it was the same density of air, then we'd locate them pretty close to the same elevation as where our piping is located. So density is a very important consideration to understand with regards to flammable gases and vapors.
All right, great, Bob. Here's the other poll. You just spoke about this. Let me launch it for you guys. You can answer. What is the Tcode for the as a maximum relevant surface temperature under normal or for condition of 125 degrees C? Sure. What is the
This is a little bit difficult because you got to remember what those numbers stood for. So,
especially if you're not familiar with the Celsius scale, so degrees C, but typically,
right.
So we had you actually spoke about this, so
I actually used this perfect example.
You mentioned the answer.
I did mention
you used this example, so the answer. Yeah, you mentioned very clearly this Tcode, and as soon as I said that, the correct answer started to increase. I can see your answer, guys, as they go along. Great, but while we get this answer, you mentioned 20 microjoules will take to ignite 90 microjoules hydrogen in the worst case scenario.
Right.
Give me another example of that. What is, like, if I drop my pen, or what does he mean?
How much energy is 19 microjoules?
Yeah, I'm just wondering myself.
Boy, I'm trying to think of a practical example of microjoules.
What if I take a hammer and, you know, a small hammer, and I go dang on my desk like this? Would that be enough?
You actually could create enough, but it would have to be probably a ferrous metal, okay, a sparking type metal. So if you took a hammer against an anvil, right, you could definitely create more than 19 microjoules energy by doing that. So yeah, that mechanical impact. I mean, you could have a situation if you took an aluminum ladder, right, and you banged it against something that was a rusty material and hydrogen was present, that would be enough energy to create an explosion.
All right. Yes, your answer, guys. Yes, the correct answer was T4, right, Bob?
Yep. T4.
And I would say that only 45% of you got the right answer. So
that's
be
okay.
careful with that.
It's okay.
No, because selecting the right product for the right atmosphere is very, very critical. You know,
it is very important. Yeah, it is very important. And we try to make sure that, obviously, when we teach our students in the classes, I hammer this home. I said, you know, by the end of the week, when you're all said and done and you've gone home and everything else, the one thing you will remember is T6 is 85 degrees, so forth and so on. So it is one of those things, if in the EX world, you definitely want to have a good handle on.
Right.
So we talked a little bit about area classification and with density of the gas and the Tcodes and all that other good stuff. So this is also out of the GMI wall chart. So we categorize a place that we're talking about that in effect, that could be a continuous period in which gases or vapor are present. We would consider that to be a zone 0 environment. If it's an environment which is only there occasionally during normal operation, we would consider that to be a zone 1. An environment in which it's not present during normal operation, but can be there for very short periods of time, we would consider that to be a zone 2. The same thing holds true for dust. Instead of zone 0, it would be zone 20, 21, or 22. And then under ATEX, there's some requirements for the manufacturers from a marking standpoint. So we won't go into all the details on that, but there's some of the marking requirements that you will see. And then on the far right-hand side, you'll see what are called equipment protection levels, which are things like GA, GB, GC, so forth and so on. So we use the IEC 60079-10-1 for gases and vapors, but there's also some other documents out there for area classification. The Energy Institute, IP15. Also in the United States, we have our recommended practices published by API. And then we also have what is called the NFPA 497 document. So they're all very similar. They all do, there are some differences, but they all are basically doing the same thing, trying to categorize the quantity, the amount, and classify these areas so we can better select equipment to be able to be used in those facilities.
Okay, next.
Okay, so there is our category designation, and this is actually per the ATEX directive. So M1 or M2 are mining applications. 1, 2, or 3 are surface equipment groups. So it's either 1G, 2G, 3G, and that would be for gases. 1D, 2D, 3D for dust. Under the IEC EX, we basically have equipment groups. And actually, that's a little bit misleading. It should be, well, actually, no, it is. It's DA, DB, DC, as opposed to 1G, 2G, 3G under ATEX. So IEC EX, it basically means the same thing. The categories under ATEX or the EPLs under the IEC EX mean the same thing.
And your protection levels?
Right. So what we classify, since we're saying a zone 0 environment is an area in which a flammable gas or dust will be present continuously, we require equipment to have a very high fault tolerant level, meaning that equipment that's approved for that environment, in effect, must be double fault tolerant. So sometimes people will ask, what's the difference between an EXIA and an IB intrinsically safe barrier? Well, an IA barrier is a 2 fault tolerant product, where an IB barrier is a single fault tolerant. So there's not nearly, well, there's not the redundancy built in to a piece of equipment that's IB as there is in an IA. So for example, an IA barrier will have 3 independent Zener diodes, where maybe an IB might only have 2. So that's why you find EXIA equipment generally is a little bit more expensive, but it also has to be a much higher fault tolerant. Next.
Yeah, and it's more, can be used, throughout all the
That is
gas
correct.
group, and so it's easier to go that way typically. But there are some other differences. Oh, here we go. Another poll question, guys. You get this. Let me launch it. Yeah, we were just talking about this all a few moments ago. So I hope we had mostly the right answer. So what is the definition of zone 1? It is whether you have hazardous atmosphere present frequently or continuously. Hazardous atmosphere present occasionally or during normal operation, or it's not present occasionally but infrequently, or where dust hazardous atmosphere present. Okay. Where do we find what is the zone in National 461? I cannot read the audience. Okay, so yeah, I would discard the last one. Bob, or am I making a wrong assumption here?
So on the last one, that's a dust hazard, right? And so
Right.
a dust hazard would be, in that case, it'd be a zone 21 hazardous environment. So
yeah,
we can,
right, 21.
we can,
yes,
we
not
can
one.
rule
Yes,
out
you're right.
D, right?
Yeah. We can rule out D. Yeah. Yeah, you can play. It's A, B, or C. But Bob gave us a good indication of that. Where 1, when you have 0 is worst case scenario, 1 is middle case, 2 is, easiest or, less dangerous, if you wish. Not less dangerous, but less likely to be dangerous, right? Let's say like that.
Yeah, it's
So
more
we basically.
Yeah, well, here's a little bit of a misconception. It's the thought process is that a zone 2 environment, if we have an explosion, it's going to be less dangerous, right? That's not really the case. It's an explosion is an explosion is an explosion, right? An issue. It's just less likely under a zone 2 environment, but the consequences of a potential explosion could be the same, whether or not it's a zone 0 or zone 2.
Correct. Yeah. So going on that assumption, we stop and show the result. If 0 is the most likely and 2 is the less likely, in between you have 1.
That's
which
right.
will be answer B. Is present occasionally during normal operation. It can happen, but not frequently. Not frequently or continuously.
It's considered to be
like, for example, outside the relief valve.
That's right. A relief valve or something like that, or a sample point, or a vent that you might have on the top of a tank that's actually containing a lot of flammable liquids. It's considered to be, it's present occasionally during normal operations. Things that you might see, like what we saw, that drawing that I showed, that those flanges of the pipe, we would consider that to be a source of release, but that's typically going to be a zone 2 environment, right?
Will only happen if there's a leak in the flange or something goes wrong.
That's right. It's not something that we would expect under normal operations, but it could happen. And so we want to take that into account. So without going into all of the various protection concepts, because we are limited on time, I do want to at least mention a couple things. The EX protection concepts are broken down into 4 main categories for gas and vapor protection. So we have energy limitation, right? And again, think about what we're talking about with regards to hazardous location equipment. We've got a triangle that we have to deal with. We want to remove or eliminate one or more legs of that triangle. So energy limitation, we're basically removing that spark, right? We're keeping it low energy. So intrinsic safety is a prime example of that. Non-sparking, again, another means we're saying no sparking. We're assuming there's still fuel present, there's still oxygen or air present, but there's no sparking, then that's considered to be increased safety. Containment, here's where we're talking about flame proof, where we have an arc and a spark, we have a fuel, but it'll be contained on the inside of, say, for example, a flame proof enclosure, or maybe a sand or quartz filled, which is also considered to be containment. And then separation, we're keeping any flammable gas outside of the particular enclosure. This could be pressurization, oil immersion. That's separating, we're keeping it away from any arcing or sparking devices. So all of these protection concepts that we think about, they all fall into those 4 different categories. Dust hazards, we do the same thing, energy limitation or separation. And again, you'll notice on the chart, those standards that are referenced there, the 60079 standards. A lot of people say, hey, I need to really know the details of, say, for example, 60079-1, which is the standard for flameproof. Well, it's really important for the manufacturer to know that. It's not necessarily important for the user to understand that standard. The standard you would really want to be following, and the standard that we talk a lot about in our classes and teach about, is the -14 standard, which is your design and application standard, and 17, which is your inspection standard.
Oops,
So-
sorry, I don't know what
No,
I
no.
did. I clicked. I went
That's
to.
okay. No, no.
I think
So-
that's the right next slide. Yes,
Yeah.
here we go. Sorry.
Yeah, that's energy limitation. We're limiting the amount of energy below the minimum ignition energy. And it's divided up into different ranges, EXI-A, IB, and IC, depending on the fault tolerance. So non-sparking is increased safety. There's also a lesser form of EXE. It's now known as EXEC. And EXE will now be known as EXEB. So they've added the EPL letters to the end of the protection concepts. And you're seeing a lot of that in some new marking requirements that came out. Containment, again, flameproof, which was commonly known as EXD, now it's known as EXDB, powder filled, enclosed break. They contain the explosion and do not allow the hot flaming gases to ignite surrounding atmosphere. And then I think finally we have separation. Yep. So encapsulation is that we're maybe using something that contains a resin. We're hermetically sealing it, pressurization, oil immersion, restricted breathing. So again, we're removing the flammable atmosphere away from the ignition source by various protection concepts.
Okay, Mark.
So markings, right? Just briefly going through this. On the very left-hand side, you'll see a CE mark, a 0575, and an EX. Everything that you see where it says under directive marking, that's a requirement under the ATEX directive. So any product must have a CE mark, an EX, and an hexagon, a 057, which designates who the notified body is, then the equipment group, equipment category, and gas atmosphere. So Roman numeral 2 means above ground. Equipment category, in effect, means a zone 0. And then G means for gas atmospheres. Then what you see on the right-hand side, starting with EX, that's your EX marking string. Yeah, so the standard marking string that you see on the right-hand side, starting from EXIA, 2C, T4, GA, that's your requirements under the IEC-EX scheme, and it's also a requirement. It's the same marking string under the ATEX directive. So then what you see down at the bottom, starting with your certificate information, you'll see an ATEX certificate will look like what you see there, a BVS 14, ATEX, so forth and so on, your IEC-EX information, and so forth and so on. The important thing to note on labels, and this is really important, especially if you're doing design and inspections, the X, that means that it's a condition for safe use. So that means there's something about that particular piece of equipment that in order to be used safely, it must be installed in accordance to whatever it states in the not in the standard, but in the certificate. So it's important to understand that. Okay, next slide.
Okay. Why can I not move forward? Here we go.
Yeah, there we go. I realize this may be very difficult to see, and I don't have my marker here, so I can't really highlight some things, but this is a typical marking that you would find on a product. This happens to be a GMI barrier. So the very top string that you see there, you see Roman numeral 2, 3, you see parentheses 1, G, EX, NA, then you see brackets, IA, GA, 2C, T4, GC. In effect, what that's telling us in so many words is that this product can be installed in a zone 2 area, but it will provide downstream protection into a zone 0 area.
We do have a question here that you might be able to answer. It says, is CE marking always required for an ATEX ICX product?
It's always required for an ATEX product. It's not a requirement for an IECEX product. And now that being said, CE markings, just because it has a CE mark doesn't necessarily mean it's compliant to the ATEX directive, because there's, I believe, 26 different directives that are in place within Europe. There's what is called the Toy Safety Directive. There's the Low Voltage Directive. There's the EMC Directive. There's a whole bunch of them. And any product that falls under the scope of those directives is required to have a CE mark. So
sorry, yeah. Go ahead, no. Sorry, Bob.
So it's a requirement to have an EX and a CE, and that's telling us that it's compliant specifically to the ATEX directive. Your Apple iPhone or something like that, you'll find a CE mark on it. That's not telling you it's suitable for hazardous locations. It's telling you, in effect, it's compliant with a different directive. And in that case, it would have been the electromagnetic noise or EMC directive.
Yeah, for European standard. So how about certification? Do they expire? I can answer this question. I know certification do not expire, but the standards change.
That's right. Yeah. So, and I think we have an answer to this on some of the Q&A a little bit later.
Okay, great. So we'll move forward. Here is another example of a marking. I think you can see it.
Yeah, and to be honest, Paulo, we can probably move along this because this is more or less telling us. Now, this marking string is somewhat difficult. It's actually one of the more difficult marking strings that you would see. So maybe we'll just.
You mean on this pole?
Yes, for this pole.
Okay. So it'd be a tough one to answer.
It's a very tough one. Yes. But I can eliminate something. Let me share with you this.
Let me say I launch it. I need to hold in one screen today. So what best answer describe this marking? Oof.
You can do the process of elimination because EXDB is the indication for a flame proof.
Flame proof, yes. D is flame proof. You're right.
So you can definitely.
So you can say that the last question is definitely wrong.
The last answer is definitely wrong.
Definitely, sorry, the last question. Yep.
Yep.
Then what do we have? We have. I'm not sure, but what I can read the entire string. Here we go. IA in bracket. Something in bracket means something inside, right?
That's right.
It's not so EXD. We're talking about a flame-proof enclosure. So something inside is IA, so it's intrinsically safe. And then we have second C, so the gas group can be used, and T6 is the temperature code.
Right.
And GB, or GA. Well, there I got lost.
So GB is telling us that this product can be installed in a zone 1 area.
Okay.
The GA in parentheses is reflecting what is in the brackets as the associated apparatus.
Which can be from zone 0.
That's correct.
So flame-proof enclosure for 2C gas located in zone 1 area containing associated apparatus. Flame-proof enclosure for 2C gas located in zone. Flame-proof enclosure. increase. I guess it's A, the correct answer.
I would say yes. Well, let's see what the poll said.
Says the poll said, well, majority of you, wow, I'm impressed, guys.
Very, very good. Yeah. So you're right. That basically officially, anytime you see brackets like that with an IA, that's considered to be the associated apparatus. And that's mounted inside of a flame-proof box, but it's providing downstream protection into a zone 0 environment. So you have a flame-proof box that's mounted in a zone 1, but yet the bracket or the parentheses where it says GA is actually saying that the associated apparatus is providing protection into a zone 0. So there you go.
Okay, what we get this seal wall chart?
Yeah, I'm not going to explain that.
So, yeah, what we bring in this? You were saying the seal is also relevant in this product, I guess, right?
It is. Well, yeah, functional safety, actually, everything within the EX world, there's a lot of overlap between functional safety and EX safety. And you're going to see more and more of this because in effect, what we're doing with hazardous location installations and applications, it's a risk assessment. And functional safety, that's basically what we're doing. We're making a risk assessment, and we're putting down, in effect, under functional safety, we're trying to now, how do I want to say this? We want to categorize how reliable and how safe is safe. And we want to put that down in percentages and do the calculations. And that's what
and that's why you see today barriers or any of these products that are used in the EX environment will carry a seal number, so seal 2, seal 3.
Yep, and it has to deal with,
you're doing a risk assessment, as you say, and you say, well, my risk is very high. I need to reduce that risk a lot, and so I need a product that allows me to do so. Or there's more reliable, but more than reliable is more. The higher the seal rating, the less likely it is for that product to fail its safety function, the function is intended to do. So if it is so a relief valve intended to open for relief, when you have an high pressure, what is the probability it will not open when that high pressure is present? Well, if that probability is high, then your seal level is very low. If the probability is very, very low, and we're talking about 0.000, very, very small numbers, but yeah, it's a completely different topic. We do have a lot of webinars on seal with our seal expert. You can guys look them up. Okay, summary. So we can go to question and answer, I guess, soon. Remember that we are looking at equipment. But
so mechanical equipment, we briefly mentioned the 60079 standards, but there are now 80079 standards that were developed from the original Senelec standards, and those are now addressing mechanical equipment for use in hazardous locations. So just be aware of it. It's out there. You're starting to see it from more and more clients, and regulatory agencies are starting to require this. So again, more knowledge that we can have, by doing these webinars, and iron sharpens iron. It just makes sure that, we're only as strong as the weakest link. So we don't want to be that weakest link, right? So.
Okay, great. So maybe stop share this, and let's see if I can. Now we'll take a little bit of time. Let me try to share the question and answer, because you guys provided some questions through the registration process, and we have provide answers to them. But you can also give live questions, and Bob can try to answer those. Okay, so question and answer. First question. Yes. We are doing a project in Korea, which is also a live question, requiring KC, KTL certification. Can ICX equipment be used without any additional testing, or do we need KC approval equipment?
Right.
Well, I know we have certified to that standard, so I'm not sure. What is the correct answer, Bob?
Yeah, so if a manufacturer already has IEC EX, it still would require additional steps to obtain Korean explosion-proof certification. So there are 3 organizations in Korea, KOSHA, KGS, or KTL, that can issue an EX certificates. So if you have an IECEX, they'll want to see the test report. They'll want to do an audit, and they may require some additional testing. However, the Korean standards are based upon the 60079 set of standards. So generally speaking, for the most part, from a product standpoint, it won't have to be redesigned. It's more of a time and money issue.
Yeah, in our experience, we do sell a lot to Korean, but you can see there's two, I guess there's two issues. Korean re-export, you have a lot of EPC that do work around the globe, so they don't care about a KTL or KGC marking, but local installation might require, and we do have requirement for our product when we supply and to be certified, and we go through this process, and has been so far only reviewing of our papers, reviewing our certification, report, and so on.
Yeah, if you don't have, say, for example, an IECEX test report, or you don't have certification on that, then yes, it would be a lot more
difficult.
Yeah.
So I think this question is also came along. How long the product certified tool can be sold, or no? Or what do I need to make when the standard changes?
Right. So if we look at this slide here.
Yeah, I got it.
Yeah, so this is, and it's a great question, and it comes up every now and then. So EN standards do ultimately get withdrawn, right? And they are published by the European Commission, and they put out the official journal, and you can do a search on the official journal. So I did a search on the official journal, specifically under the 79-15 from 2010, because that is not the latest standard, and it does not show a date of withdrawal. So I can't answer that question, because on the right-hand side, it would actually say there is something in there that says this will be officially withdrawn. And then that is up to each. It's basically telling each one of the countries as part of the European Union, okay, guys, you need to ultimately withdraw this standard because it is no longer valid, right? Yeah. Now, the question that's somewhat related, but under IECEX, people ask, do I have to get a product certified to the latest edition? And not necessarily. However, it says a new or initial IECEX shall only be issued to the current standard or one edition prior. So if you're looking to get something certified around the IECEX scheme, it makes sense to do it to the latest edition, obviously, but there is a little bit of a fallback to allow you to go one edition prior, okay?
Yeah, in fact, we have products that have been certified to a standard which has not been withdrawn yet, right. But there is a new standard. You can still, sell them, they're still valid. And however, of course, when you make a new product or the standard is being withdrawn, you have to recertify.
Right.
Okay. What is mechanical protection around coupling? What material can I use? Well, that is a question for you, Bob. I know.
Yeah. No. Well, and I'm not sure if I'm answering the question correctly here, but this was what I was thinking. So in the 80079-36. we talk about possible ignition sources, and it's very similar to what we talked about previously: hot surfaces, stray currents, static. So we want to look like around couplings, we want to evaluate the materials, if you will, to make sure that none of those materials around a coupling, right? And a coupling potentially can create friction. So we want to make sure that the materials that we're using are considered to be materials in effect that will not overheat or will not create friction, or if they do, we're addressing it in some way, shape, or form. And there's some specific details on how to address mechanical equipment in -36.
Not 100% sure about this, Bob, but I know that, for example, some of the material we have to use, for example, the plastic, has to follow a certain standard. For example, you cannot have built-up static, so there are certain mandated regulations. You have to have certain
amount of carbon,
additives to hit. The aluminum you're using for aluminum casing has to have a certain specification. You cannot just use any material because
correct. That's correct.
But I imagine there are standards to be followed. Okay, so is there an equivalent to ATEX in the US? Well, I guess so, or not. I'm not sure.
Yeah, this comes up every now and then, or is ATEX allowed in the United States? And ATEX is a European directive, and we don't recognize ATEX in the United States. Um, um, it's not to say that people haven't used ATEX equipment in the US. One of the issues with Deepwater Horizon that came out of that the US Coast Guard found that there was a lot of ATEX equipment on a lot of these rigs operating in the Gulf of Mexico. And they changed the rules and regulations after Deepwater Horizon to basically state ATEX is no longer allowed. And part of the reasoning was because under ATEX for Category 3, Zone 2 equipment, you can actually do a self-declaration. And the Coast Guard said, we don't want that. So in the US, we're governed by basically 3 regulatory agencies, OSHA, BSEE, and the US Coast Guard. We typically will follow the NFPA, which is considered to be our national electric code, or we'll follow API recommended practices, or we'll follow the Code of Federal Regulations that are published by the federal government, depending on the location of type of facility you operate in. So, and ultimately, it's up to each jurisdiction. The authority has jurisdiction as to what they will accept.
Okay, so the next question is on cable. Under ATEX, is it mandatory to use armored cable? I haven't seen many armored cable here in Europe, so I guess the answer is no, but I'm not sure.
Well, there are some requirements within some of the EN. So for example, that EN 61892-7, that EN standard, that's specifically for MODU, mobile offshore drilling units. It specifically says you must use armored cable for Zone 1 or Zone 0 applications. Now, generally speaking, the EN standard for hazardous location is the -14 standard. And while it recommends that you use armored cable, it doesn't state specifically it must be armored cable. And cables don't fall under the scope of the ATEX directive. The important thing to note with regards to cables and hazardous locations, the reason why the armor is there is to provide a mechanical protection. However, you can provide mechanical protection in other means besides armored cable. We can protect it by location. We can protect it by the use of an open conduit. We can protect it by the use of trays. There's various means to protect cables. So again, armored cable is widely used. Yeah, and by the way, I threw in there under ATEX directive, there is an exception such as heating cables. So heat trace cables does fall under the scope. So cables themselves are not considered to be potential ignition sources. So it falls outside of the scope of the directive.
Okay. One more question. Can I install ISB, so intrinsically safe barrier, in a Zone 2 environment? I think you can.
Yep.
If they are certified for it.
That's right. So a lot of barriers, like what we saw with the GMI marking, that barrier was actually approved to be installed in a Zone 2, right? So we could install it in a Zone 2 environment. We would have to put it in a certified EXN enclosure, and it is perfectly allowed. However, if we had to install a barrier into a Zone 1 environment, well, then we go back to either a flame-proof or we look at a pressurized enclosure. And there may be some instances where we required to do that as opposed to having them all located in a safe area, because part of the evaluation is the length of the capacitance or the length of the cable with capacitance and inductance. We want to try to keep the field device as close as possible to our ISB. And sometimes if the panel is located in a safe area and it's 1,000 meters away from that transmitter, besides voltage drop, we also have to take into account the capacitance and the inductance on that circuit.
Plus, there are some installation where everything is in the hazardous location, you know.
That's right.
So,
That's
and the barrier itself cannot go into a zone, for example, on a not a rig, but hips, for example, or something where you and you want to contain it next to it. Okay, so let's see if you have one more question here. Sorry, I went too fast. How to select device suitable to be used in a particular area, example, Zone 2, second A plus, second B, T3.
Yeah.
That's a tough one. Okay.
So there's that label again. So by looking at that label, what zone is this suitable for? Well, the 2G, the ATEX 2G, and the GB is telling us it's suitable for zone 1 and zone 2. So that's telling us, it doesn't say on there specifically zone 1 or zone 2, but that's telling us that. The gas, in this case, it's marked 2B plus H2, so it would be suitable for a 2A, 2B, and hydrogen gases. The Tcode, it has a T5, so that's better than the T3, which is requirement. The ambient, in this case, is rated for -20 to +50. It's certified under ATEX and IECEX. And then finally, what is the IP rating in this? It is IP66, suitable for hose down locations. So it would be suitable.
Okay. Okay, we have, well, we typically get this question all the time. We want to know about something else, so, well, you can look up our website. We have webinars, live webinar coming up. We also have recorded webinars, all the webinars, including this one, which I'm not sure is going to be put on once our marketing team reviews it and see all the mess we made today, Bob. But typically these webinars are recorded, and they go on our Zoom, on our YouTube channels. We do have a couple of questions while I put this poll on. Live question: in battery room, what kind of ATEX material used? Not sure about this question.
Well, I'm assuming, are we talking, so batteries are considered to be potentially, they can vent, and they certainly can create, in some cases, hydrogen gases. So battery rooms typically are classified as a hazardous location. They could be considered to be a zone 1, 2B plus H2 type environment in many cases, and that's what I have seen. So you might see that in a lot of battery rooms. However, part of the classification, you can also, you can ventilate rooms. So you could find a situation where you're eliminating a lot of the vapors through that room. So that's the kind of material you would find. You would probably find battery chargers or something like that that might be flame proof, or they may be located out of the battery room. You would certainly, if there's any lights in the battery room, that you would want them certified and that type of stuff.
How about cathodic corrosion protection?
Yeah, well, that's a whole nother topic, but cathodic corrosion protection, I would say this much with regards to EX equipment. The biggest issue that we find with potential corrosion, and it somewhat relates to cathodic protection, is dissimilar metals. And this is a big issue with cabling, cable glands going into an enclosures. So actually with the session that I'm doing with these gentlemen right now, we're kind of in that area. The big issue is if you take a brass gland and you install it into an aluminum flame-proof enclosure and you put it in a saltwater environment, then all of a sudden the aluminum enclosure acts as a sacrificial anode. And so we don't want to see that. So you want to typically use a nickel-plated brass. You certainly want to use things like thread lubricants on any of the joints. So we want to see that type of stuff with regards to providing cathodic protection. But it's a whole slew of different things that you can get
Maybe
into.
one day we'll make a webinar on that. As usually, Bob, your knowledge is outstanding. I'm sharing the result. We didn't get all excellent today, but it's expected. Firstly, my fault, my presence, also this technical issue. But thank you, guys. We didn't get any poor, so that's great. I will close this. Here's our contact. I will show it for a second. So when you look at the registration, you can see it. Stop share. We are here. We're 10 minutes into it, but thank you, guys. Thank you, Bob, again. Sorry for the issues. Keep safe.
My apologies. I'm glad we were able to make through it. So
yeah, we made it. Very good. We'll talk soon, Bob. You guys you will get copies of the slides, registration, everything else. If you have any question, you can just send us an email. Again, Bob, thank you. I'll go to my wife.
Yes, there you go.
Okay, ciao, ciao.
Ciao, everybody. Thank you so much.
Ciao,
Bye-bye.
ciao.